In this unit, we're going to continue our discussion of spectroscopy and using instrumentation to help us really figure out the structure of a compound. We've looked at IR spectroscopy, which will help us identify functional groups. We talked about mass spectrometry, which the main function was to look at the molecular weight and we could look at the fragmentation patterns to give us some idea of structure. But what we're going to focus on in this new unit is something called nuclear magnetic resonance, or abbreviated NMR. And this is really going to help us actually look at the connectivity of atoms in a compound. Now, just to kind of highlight something real quick about this type of spectroscopy, notice here the magnetic resonance, the M and the R in that. Um, where have you heard that before as well? How about the type of medical analysis known as magnetic resonance imaging? And MRI operates on the exact same principles as nuclear magnetic resonance. In fact, they're pretty much the same analytical technique. And the reason why they don't call it nuclear MRI or nuclear magnetic resonance imaging is people get a little freaked out when they see nuclear and they think, oh, radioactive or something like that. And in reality, this has nothing to do with radioactivity. Nuclear just refers to nucleus. And that's what we're looking at. We're looking at the nuclei of certain atoms. Now, since this is a form of spectroscopy, it's going to use a certain portion of the electromagnetic radiation spectrum. And in this case, it's going to utilize radio waves. And like infrared spectroscopy, this is going to cause some change in the molecule. For IR spectroscopy, that was the increasing, or I should say, the increasing the vibrational modes of the bonds. And in this case, for NMR, what we're going to be measuring is the energy change involved in the flipping of nuclear spins. And the final result is that we get to know more about the environment a nuclei is in. And ultimately, that's going to lead us to the structure of the compound. And we are, since this is organic chemistry, we're going to focus specifically on carbon and hydrogen nuclei. That's what's in that's what is in every organic compound. So what information does this give us? We'll be able to know the number of unique types of carbons and hydrogens, the number of hydrogen atoms attached to a carbon, and ultimately the connectivity of the carbons and hydrogens together. So what nuclei can be seen using NMR? Simply, this is any nuclei that has an odd mass number. So that includes protons, carbon 13, fluorine 19, phosphorus 31, etc. And we're just going to focus on in this unit carbon and hydrogen, while the other ones are more kind of specialized, more for specific types of research. But I want to highlight that NMR cannot see like deuterium or carbon 12, which, by the way, carbon 12 makes up about like 98 some odd percent of all carbon atoms. So when we're looking at using carbon NMR, we're really looking at like literally 1% of all carbon atoms because we can see carbon 13, but we cannot see carbon 12. So how does NMR work? I'm going to spend the rest of the time in this video just talking a little bit about the theory behind NMR. And this works great in a class setting, but what I want you to do for right now is kind of close your eyes and imagine some things with this exercise. But nuclei that have an odd mass number have a spin. We learned this back in general chemistry. And what makes the odd mass number ideal is that it has only two spin states. If it's some other mass number combination, then it either has only one spin state, which doesn't work. I'll tell you why in a little bit, or it has too many spin states and it gets really super confusing. So those spin states we're going to label as either plus one half or minus one half. Now, the reason why these two spin states are ideal is that there's one difference in energy between them. One of these spin states is low energy, and the other spin state is high energy. And remember, spectroscopy is about measuring the energy difference behind some sort of transformation. Okay, so here's where your imagination needs to come in. I want you to imagine that you are a hydrogen nuclei. You're not bonded to anything, you're just a free-floating hydrogen atom, and you're in a room with 100 other hydrogen nuclei. And what I want you to do is kind of close your eyes. And if you are right-handed, I want you to stick your right hand out in some random direction. And if you're left-handed, I want you to do the same thing. And so when you are in this room with other hydrogen nuclei, okay, maybe you open up your eyes, you see there's 100 people in this room, and they all have their hands stuck out in a random direction. So some of them are like this, or like this, or like this, or maybe this way, or maybe that way, and so on and so forth. But you'll notice that most of you that are right-handed, most of the people in that room have their right hand stuck out in a random direction. And then a few, maybe five or six, are left-handed, and they have their hand stuck out in a random direction. Now, what I want you to do is think of if you are right-handed, you are the plus one half spin state. Most of you are at that lower energy level. And those of you that are left-handed, you're the minus one half spin state, and you're at that higher energy level. Okay. But as I said before, all of these nuclei in that room, your hands are oriented in a random direction. Now, why is there something magnetic in NMR? Why is there something magnetic in MRI? When you place these nuclei, so now you're all in this room, and now you're all going to be put in the middle of a very powerful magnetic field. And that's going to align all of your spins. So essentially what I want you to do, stick your hand back out in a random direction, and I want you to imagine as soon as you're exposed to that powerful magnetic field, everybody's hands, regardless of whether they are left-handed or right-handed, is going to go straight up in the air. And so you're all aligned in the same direction. So it kind of looks something like this. So these are plus one halves here. And then we're going to say this is the minus one half. And then we got some more plus one halves, and then maybe another minus one half. But notice you're not now you're not oriented in a random direction. So imagine your hand is straight up if you're right-handed. If you're left-handed, your hand is straight up. Now, the energy change hasn't happened yet. I have to get all of these nuclei that are plus one half spin state to flip to negative one half because that's going to go from a low energy to a high energy. And this is where the radio waves come in. Radio waves have the right frequency, the right wavelength to cause this energy change. So then I'm going to expose all of these to radio waves. And what's the end result? The end result is all of the nuclei have now flipped their spin state to minus one half. So if you are right-handed and your hand is straight up, what I want you to do is put that hand down and put your left hand up. And then again, close your eyes and look around this room. You'll see that every single person in this room has their left hand straight up in the air. And what happens is the NMR machine reads that difference in energy and gives us some sort of output that tells us the environment that the hydrogen nuclei are in. So these nuclei that are in the 1/2 spin state plus 1/2 are precessing at a particular frequency. And when radio waves or radio frequency, RF, with the right frequency that those plus 1/2 spin states are precessing, it causes resonance. And I'm not talking about resonance at the beginning of the semester where we're using arrows to push electrons around. This is a different kind of resonance. Okay, so I want to emphasize that. This resonance is about flipping that the nucleus absorbs energy and flips to the higher energy, excuse me, higher energy spin state, mm, which is the minus 1/2. Now, the more powerful the magnet is, so here we have a magnetic field at about 1.41 Tesla. And this energy change is a certain amount. But if we get a more powerful magnet, here, about 7 Tesla, the energy change is greater, and that's going to give us more resolution, which just means we have better looking spectra. Now, obviously, and if you have your hands still up, go ahead and put them down. Sorry. Um, Obviously, the more powerful the magnet, the more expensive the machine. But let me just look, let's just take a look at a kind of a flow diagram here of how this works. And typically your sample is placed into something called an NMR tube. So it's a long, thin tube. It's bigger than a capillary tube, like a melting point, but it's pretty thin. And we put a little bit of sample in here, and then we dissolve that sample in a liquid that is usually what we say is deuterated. All right, the solvent is deuterated, which means that all protons are replaced by deuterium in that solvent. And think about why that's the case. If all of the hydrogens, if NMR is designed to look at protons, 1H, and you have a little bit of sample, but mostly solvent that also has protons in it, what is the NMR going to focus on? It's only going to see mostly solvent and very, very, very little of your sample. So if the solvent doesn't have any protons, either by design, like for example, with say carbon tetrachloride, or one of the most common solvents that's used in NMR spectroscopy is deuterated chloroform, where the hydrogen in chloroform has been replaced by deuterium. That's the D there. Then the machine won't see your solvent. The only thing it sees is the sample that's dissolved in the solvent. So that NMR tube is dropped into the middle of the very powerful electromagnet. Now, usually these magnets have to be supercooled either by liquid nitrogen or by liquid helium. And in fact, if you ever see like a very high-powered NMR, we don't have them here. We have lower-powered NMRs in our labs. You'll see like a lot of warnings on them, like don't hug this machine if you have a pacemaker, or don't put your credit cards up to the machine because it'll erase all the data. But it's a very, very, very powerful electromagnet in there. And so the NMR shoots a bunch of radio waves at your sample, and that causes some sort of signal to be sent to a computer. And the computer does a whole bunch of advanced calculations. It's called Fourier transformation. Don't need to ever worry about doing those. That's why we have computers. And it spits out a spectra to it, out of it that we can interpret and figure out what the structure of that compound is. Now, these are some pictures of some NMRs at the school I used to teach at, and kind of give you an idea of the, kind of the difference in their appearances. This one over here is a really old machine. I think we have it in storage now. It's kind of a dinosaur. And you can see here the output on it is not even a regular computer screen. It looks like kind of an old school EKG, like a black screen with green uh, lights on it. And the printer here is not really a printer. It's called a plotter because it's got a bunch of individual like ink pens that would literally just kind of like plot the spectra on a piece of paper. So very, very old school. Um, Another one that my former institution has, much more high tech. You can kind of see it looks a little bit more like the diagram from the previous page, but that's where the electromagnet is housed, and you can kind of see their danger over here. But it kind of takes up a couple of rooms, one for the machine and one for all the like ancillary machinery that's required to keep it super cool. Um, and then this is an example of something known as benchtop NMR. It's not as highly resolution or as high resolution as the more high-tech versions, but it's great for teaching organic labs because they're very user-friendly. They don't require liquid helium or nitrogen to keep the magnet cool inside. But we're actually going to be using these in lab if we haven't already. We'll be using some benchtop NMRs. In the next video, we're going to jump right into interpreting NMRs and what are the important skills that you need to develop to correctly interpret NMR. But that's for the next video.